Так, добрый день, давайте начинать лекцию. So we will first discuss a new necessary condition for existence of codes, which is called the improved Singleton bound. So recall that the normal Singleton bound, not improved, looks like that. The dimension of the code plus the minimal distance is at most the block length plus 1. And the improved Singleton bound is obtained when we put some multiplier greater than 1 in front of D. More precisely, it looks like that. K plus Q over Q minus 1 times D. And this number can be actually not integer, so we round it up. We take the floor or ceiling. Anyway, let's postpone it. Is at most n plus some small logarithmic, terms. More precisely, it's log base q of 2 times q minus 1 times n. The important thing that it grows very slowly as a logarithm function when n increases, so we can actually forget about this term when n is large, and then the improved Singleton bound is better than the normal one because of this factor. So for example, if q is 2, then this is just 2. So instead of d, we have 2 times d. And the improved Singleton bounds is an easy corollary of the Plotkin bound. So recall the Plotkin bound. So the Plotkin bound, I mean the second Plotkin bound, says that if we have the code with parameters n, k, d, and d is at least q over q minus 1, q minus 1 over q minus 1 over q times n. So for example, in the binary case, this is inequality reads that d is at least half of n. Then the dimension, actually the number of code words, which is 2 to the k, is at most 2 times q minus 1 times n. Or in other words, the dimension is at most the logarithm of this number. Sorry, not 2 to the k. In general case, it is q to the k. The number of code words in general case is q to the k. So k is at most the log of 2q minus times 2q minus 1 times n. And this logarithmic term comes here, as you can guess. This is the same term as this one. And so that bound can be easily derived from this one. So, and here is the proof. recall the proof of the normal Singleton bound. In that proof, we transform an NKD code to n minus t k minus t d code by fixing, say, the first t positions in all the coordinates. So we take the most popular t length t prefix of coordinates. So by pigeonhole principle, there are q to the k minus t such coordinates. Then we just cut the first t letters because in all these coordinates they are the same anyway. So this cut doesn't decrease the distance, and the block length is increased by t, decreased by t. For Singleton bound, we used this transformation for t such that k minus t is 1. So that means that there are more than one code words in the resulting code. So t is equal to k minus 1, and so we obtained that the distance should be at least the block length, which is in our case n minus k plus 1. But now we will use, instead of this trivial observation that if there are at least two code words, then the distance must be at most the block length, we will use the Plotkin bound. So we will use t smaller. We use t so that the distance of the resulting code is at least q minus 1 over q times the block length, which is now n minus t. And we choose d. D is the smallest such number to obtain the better bound. And let's just calculate what this smallest d is. Sorry, we choose t the smallest t such that this holds. So we can't choose this, sorry. We can choose t. So we choose t so that this holds. In other words, n minus t is at most d q over q minus 1. And since t is n minus t is an integer number, we can rewrite this using the floor here. So this is the same as saying that n minus t is less than the ceiling of that. And in other words, so we see that the minimal such t is equal to n minus the ceiling of dq over q minus 1. And now for the resulting code for this one, we use the second Plotkin bound. That means that we know that since d is larger than q minus 1 over q times the block length, we know that the number of coordinates 2 to the k minus t is at most 2 times the dimension. That is 2 times the dimension and times q minus 1. And let's upper bound this by 2q minus times q minus 1 times n to obtain easier formula. And hence we know that k minus t is at most the log of the right-hand side, log base q of 2 times q minus 1 times n. Well, and now it remains to recall what is n. So what is t? T is this number. So in other words, we have the inequality k plus dq over q minus 1. And we take the ceiling of this. So we take the, not the integer part, by the closest integer from above, is at most n plus this logarithmic term, log of base q of 2 times q minus 1 times n. So we obtain exactly what was claimed. So this is the right-hand side, and this is the left-hand side. So we now see that here we need the ceiling, not the floor. The ceiling of all this number, including times d. Okay, so this is proved. Are there any questions about the proof of the improved Singleton bound? Okay, now we can switch. Now let's see on the picture. Let's draw the graphs of the bounds known so far to see how this bound relates to the other bounds. So for example, consider the binary alphabet. So q is 2. In this example, we had so far 3 bounds. So the Warshamov-Gilbert bound, which is the sufficient condition, the Hamming bound, which is necessary condition. We had also the Plotkin bound, which is also necessary condition. All these 2 bounds indicate that there is no code here. No code here, no code here, and no code here. And this indicates that there is code here. And now the new bound, let's write it in, say, red color, looks like that. It is a straight line from this point to this point. Actually, I am very imprecise because it should cross the Hamming bound. So let's write the Hamming bound better so that we can see that it indeed crosses it. So the Hamming bound, actually in this, here the derivative is infinite, so it's like something like that. Now it's better. So it includes something new to the area when there is no code. I mean, this part. This part, we didn't know that there is no code here. Now we know it. So ignoring logarithm term, in the binary case, the inequality is like that. K plus 2 times d is at most n, or in other words, k over n plus 2 times d over n is at most 1. So, and this inequality specifies this region, this one. So in other words, it says that above this red line, there is no code, because this is necessary condition. Так, ну есть какие-нибудь вопросы? Еще раз спрашиваю по поводу этой самой, по поводу improved Singleton bound. Okay, now we switch to a new code, which is called Bch code. And Bch code is a generalization of Hamming code. So recall that we had two families of Hamming codes. In one family, the distance was 3, and the parameters were 2 to the m minus 1, 2 to the m minus 1 minus m, and 3 over the binary alphabet. And in the second family, we had one additional bit in code words. So the block length is 2 to the m. The dimension is the same, and the distance is 1 bit more, so 4. So we will, Bch code will generalize this one. So this will be a particular Bch code actually. So the explaining of this abbreviation is the following. B is both. C is actually array Chaudhuri. And H is actually hawk, queen, ham. So it's actually hard to memorize those names. So the abbreviation Bch is easy to memorize. So the Bch code, each code in this family is specified by two integer parameters. M, which plays the same role as M in the Hamming codes, I guess, right? And also C. So for Hamming code, C will be 3. And so these are integers. And the messages in that code will be identified with polynomials of one variable, univariate polynomials like in Reed-Solomon code, but of special type. So we will consider polynomials P of one variables where the ground field consists of 2 to the m elements. So we know actually that there is a unique field of that cardinality where the degree of polynomial is less than 2 to the m minus s, and those polynomials satisfy a very special requirement. They evaluate to 0 or 1 in all the points in the field. So P of x is an F2. So F2 is a field of 2 elements, 0, 1. And as well known, F2 is a subfield of the field F to the M. For all x's in our field. So normally the polynomial takes arbitrary values in the field, but we restrict ourselves with only those polynomials which have such values. And hence we obtain a very strange set of messages, and we will calculate how many messages we have, and this will be the most difficult thing to find out how many such polynomials are there. Also we need to understand what is the minimal distance, but this is easy to understand. Sorry, I haven't yet explained what is the encoding of such message. The encoding of such message is the bit string of length 2 to the m, which is equal to the values of the message in all different points. So the code of P of x is the value of P in all different alpha 1, alpha 2, arranged in any order. We fix some order in which we list all 2 to the m elements of our field. And then using that order, we encode the message, all the messages. And so now the code is specified, and it is easy to understand that the minimum distance of BCH with those parameters is at least s plus 1, because this is the subcode of the Reed-Solomon code. And we know that if we have two polynomials of degree less than 2 to the minus m minus s, then they can coincide is less than 2 to the m minus s different points. And so the number of points where they differ is at least s plus 1. So the minimum distance of this code BCH with parameters ms is at least s plus 1. For example, if s is 3, the minimum distance is at least 4, like in this Hamming code. And now comes the difficult part, to understand how many such polynomials are there. And this task is difficult because the messages are determined by two different constraints. The first constraint is about the degree, and the second about the values. And it is not easy to understand how those constraints interplay with each other. So let's start to understand it. So how many messages? First of all, assume that there is no restriction about the degree. No restriction. There is actually that, we will assume, say that S is 0. And that means that we consider polynomials of degree. So the degree of polynomial is at most n minus 1. And in that case, there is a one-to-one correspondence between coefficients and values. So the number of possible values is 2 to the n minus 1. So the number of possible coefficients is also 2 to the n minus 1. And this, so this one-to-one correspondence in this direction is trivial. This is just computing values. In another, this is done using the Lagrange polynomial. If we know the values, we can compute coefficients. So the coefficients of any polynomial can be computed as the sum of its values times special Lagrange polynomials, call them, say, L alpha, where the summation is over all elements in the field. And L alpha has the following property. It evaluates to 1 if X is alpha and to 0 otherwise. And this polynomial, one can choose such a polynomial of degree exactly n minus 1. And that's why we need that the degree is at most n minus 1. So an easy way to construct this polynomial is just to take the product of x minus beta, overall beta different from alpha, over the product of alpha minus beta, again over beta, overall beta different from alpha. And so an easy substitution shows that if we substitute here alpha for x, we obtain 1. If we substitute any other number for x, we obtain 0. So this is how we can show that there is one-to-one correspondence between coefficients and values. And in our case, we will consider only values which are 0 and 1s. And again, we obtain that for all possible 2 to the n choices of values, we have a polynomial with such values, and so the number of messages is 2 to the n. So for s equal to 0, the number of messages or the number of polynomials is equal to 2 to the actually 2 to the n. I said n is the block length, n is 2 to the n. So we obtain 2 to the n, which is 2 to the 2 to the n. So if there is no restriction on essentially no restriction on the degree of polynomial, that is S is 0, then we have 2 to the n possible messages. So dimension is n. But now we need to understand how the dimension is decreased when we increase S. For example, what restriction on the coefficients is provided if we require that A0, the leading, not the leading coefficient of P is 0. To understand this, we will, in our case, find a more simple formula for Lagrange polynomials. So let's prove the following lemma. So in our case, L alpha of x is equal, can be obtained by the following simple formula. It is x to the n minus 1. So recall that n is 2 to the n, the block length, plus alpha times x to the n minus 2 plus alpha squared times x to the n minus 3, and so on. The last term, the constant term of this polynomial, is alpha to the n minus 1. This lemma can be understood that there is Lagrange polynomial with this property, or that the unique Lagrange polynomial with this property has this form. But it is the same, because it is easy to understand that the Lagrange polynomial is uniquely identified by its properties. So its properties is that its degree is n minus 1, and it evaluates to 1 in the point alpha and to 0 in the remaining point. But we will just show that if we take this expression, we obtain what we need. First of all, we see that the degree is n minus 1. Now we need to understand what it evaluates to in different points. To this way, first of all, we will rewrite this. So we will deduce our claim from 2 other claims. The first claim is that if we take the following formula, we obtain a Lagrange polynomial, and the formula is x minus alpha to the n minus 1. So n, again, n is the cardinality of our field, 2 to the n. Plus 1. And to understand this, we just plug into this expression alpha, and it is easy to see that we obtain 0. We obtain 1, because if we substitute alpha for x, then this term vanishes, 0 to the n minus 1 plus 1. So we obtain 1. If we substitute anything else for x, we obtain some non-zero element of the field raised to the power of n minus 1. And by Lagrange theorem, it evaluates to 1. So if beta is different from alpha, then beta minus alpha is non-zero. And when we raise it to the power of n minus 1, we obtain 1. And this is because n minus 1 is a cardinality of the multiplicative group of our field. And by Lagrange theorem, if we raise any element in the group into the power which is the cardinality of the group, we obtain 1 in the group. So we obtain 1. And 1 plus 1 is 0, because our field has characteristics 2. 1 plus 1 is 0, because it includes the subfield of 2 elements. And so if we take this formula, we obtain the desired properties of the polynomial. Its degree is n minus 1, and it evaluates to what we want in all the elements field. And so it remains to prove that this formula and the formula in the lemma is actually the same formula. And this is done as follows. So the second claim is that if we take this formula and the formula in the lemma, we obtain actually the same formula. And this can be proved either by raising this using the binomial of Newton, and we obtain here the sum of all powers. Actually, maybe plus 1 here, sorry, because I forgot about this plus 1. So if we raise this if we use the formula of binomial, we obtain the sum of these guys with certain coefficients. And these coefficients are actually the binomial coefficients. And all the binomial coefficients will be equal to 1 in our case, because our binomial coefficients will be odd for all binomial coefficients for n minus 1 in the n minus 1 row of Pascal triangle will be odd. But instead of proving this, let's consider a shorter way to show this inequality. Actually, now I'm completely confused, because actually we do not need plus 1 here, I guess. Let's see. So if we multiply the both hand sides by x minus alpha, so multiply both sides by x minus alpha. So in the left-hand side, we obtain x minus alpha to the power of n. In the right-hand side, we obtain x to the n minus alpha to the n. And we use the well-known formula, the difference of nth powers is equal to this difference multiplied by this. And actually, this is the same, because n is a power of 2, n is 2 to the n, but raising to the square, raising to the power of 2 is very easy in our field. So we have a plus b squared is equal to a squared plus 2 times ab plus b squared. But 2 is 0 in our field, so we obtain a squared plus b squared. So in our field, squaring can be done in a simplified way. A plus b squared is the same as a squared plus b squared. And raising to the power of n is just m-fold squaring. We square x minus alpha m times. So we obtain, actually minus and plus is the same. We can write it as x plus alpha, and here also plus alpha. This is the same. If we apply this inequality m times, we will obtain x to the n plus alpha to the n. And so we obtain this equality, and just by dividing it by the polynomial x minus alpha, we obtain in the right-hand side this equation, in the left-hand side this equation. So, so we obtain this lemma without 1. So I'm sorry, somehow. We obtain plus 1 because we have here plus 1. Sorry, that's a mistake. Plus 1 we obtain because here we had plus 1. So anyway, now we have a very convenient formula for Lagrange polynomials. And using that formula, we can now understand what does it mean that the leading coefficient is 0. So first of all, say that S is 1. Then we have, if we, let's denote our polynomial a of x by say a to the n minus 1 times x to the n minus 1 plus a n minus 2 times x to the n minus 2 plus etc. a 0. So if s is 1, we require that n minus 1 is 0. That is, the degree is at most n minus 2, is less than n minus 1. So, and as we have just understand, this means that the n minus 1 coefficient of the sum, so ax can be expressed as the sum of p of alpha times the Lagrange polynomial. And for that polynomial, we have the formula x minus 1 to plus alpha x to the n minus 2, and so on. Now we see that the leading coefficient of a of x is obtained as a sum of all values of the polynomial. So this is the sum of all values of our polynomial. Sorry, we have here a of alpha, not p of alpha. So the sum of a of alpha over all alpha is 0. And how this requirement decreases the number of polynomials. So a of alpha, all a of alphas are 0 and 1s. Without that constraint, we allow all different 2 to the n choices of a of alpha. So I obtain 2 to the n messages. But now we have one equation over F2. So this is one equation over F2. So how many now how many different ways to choose the values of our polynomial we have. So one equation, one linear equation determines linear subspace of dimension m-1. So we obtain the dimension one less. So in the case S is 1, we obtain that the dimension is n-1 instead of n. Так, давайте сейчас перерыв сделаем на 5 минут, потом продолжим. Так, давайте продолжим. Okay, so we need to understand now how the dimension of the code decreases as S increases. So assume that we have S is 2. Now we will see that dimension will become n minus 1 minus m. And that means that we will obtain m new constraints, equations defining our linear space. So when S is 2, we have one new inequality, n minus a n minus 2 is 0. In other words, we impose one new constraint, that is the sum of alpha times a of alpha is 0, because you see that the coefficient n minus second coefficient is equal to the sum of values of our polynomials times the points in which we compute that value. So the sum of alpha times a of alpha. So one may wrongly think that this is one equation, but actually this is one equation only when we consider this equation over the field of 2 to the m elements. But recall that our code is a binary code, so all a of alphas are actually just bits, and this is the sum of elements of our field. So, and each element of our field is actually represented by m-dimensional vector over m2. So this is actually the sum of columns of height m, if we consider those alphas as elements of m-dimensional linear space over F2. So we obtain as a result that this is not one, but m equations over F2. Which means that we have now m plus one equation. So we had one equation and we add m new equations. So the linear system has m plus one equation. So the dimension of the set of its solution shrinks to n minus 1 minus m. Now consider the next s. So when s is 3, we get one new equation that a n minus 3 is 0. And again, observing our formula for Lagrange polynomials, we see that this means that the sum of alpha squared times a of alpha is 0. And again, this is m equations, but actually these equations are not new. So they actually do not decrease at all the dimension of the set of solutions, because this equation actually follows from this one. So if we already know that the sum of alpha a of alpha is 0, we can deduce that also the sum of alpha squared of alpha a of alpha is 0. So we have the following simple lemma. So if the sum of a alpha times alpha is 0, Actually, we can just write it that this sum. I'm sorry. If this is 0, I wanted to say that always this sum is equal to the square of this sum, but this is not true. This sum is equal to the sum squared. So in general case. And this is because if we raise this to the power of 2, using the simplify raising to the power of 2, we can deduce that the square of this sum is equal to the sum of alpha squared times a of alpha squared. And we know that a of alpha squared is equal to a of alpha because we are given that this is either 0 or 1. And in F2, the square is just equal to x squared. This is the same as x. So we obtain that this is the same as the sum of alpha squared, just a of alpha. In particular, if the first sum is 0, then the second sum is 0. Which means that actually the equality a n minus 2 is 0 implies that a n minus 3 is 0. So we do not obtain any new constraint when s is 3. So we obtain that in that case, again, k is the same. So the dimension is still n minus 1 minus m. Actually, we obtain here only the lower bound because we haven't proved that all these inequalities are linearly independent. Let's write more precisely that we have these inequalities. And proceeding further, we see that if S is 4, we obtain one new equality, and that the coefficient with number n minus 4 is 0. Which is equal to the sum of L alpha cubed A of alpha. And this is again m new equations. But when S is 5, we obtain no new constraint because A with subscript n minus 5 is the sum of all alphas to the 4 A of alpha. And this is implied that the sum of alpha squared A of alpha is 0. This is implied by the equality that the sum of alpha squared A of alpha is 0. Which is already known to us. This is this constraint. It is in turn, it is implied by this inequality, but now it doesn't matter that it was implied by a previous inequality. The important thing that here we have 0 new equations. And in general, when S is even, we have m new equations compared to S minus 1. When S is odd, we have no new equations. So we obtain that in general, k is at least n minus 1 minus S minus 1 over 2. And here we need to take the ceiling. For example, if S is just 1, we obtain n minus 1. Good. When S is 2, we obtain n minus 1 minus m. And when S is 3, we obtain the same, n minus 1 minus m. So this will be our final count. So we have proven that the following theorem, that the distance, minimum distance of BCH with parameter ms is at least n minus 1 when n is 2 to the m minus s minus 1 over 2. Or if we express this n minus 2 times m, sorry, I forgot to say that every new inequality, every new constraint adds m equalities and not 1. So if we express this through m solely, we obtain 2 to the m minus 1 minus s minus 1 over 2 times m. Or if we express this through m, we obtain n minus 1 minus s minus 1 over 2 times log n, binary log n. In other words, in BCH, the message of certain length k is encoded using k bits plus log n times log n additional bits for every, more or less, for every corrected errors, because s minus 1 over 2 is the number of corrected errors by the code. Так, ну вроде бы я закончил. So, are there any questions about this proof of this theorem? Что-то вы вопросов совершенно не задаете. У меня есть большие сомнения, что понятно. Okay, now we need to understand why BCH codes are generalizations of Hamming codes. So, as I said, for S equal to 3, we obtain the same as Hamming code. So, consider this case. So, I claim that when S is 3, we obtain just Hamming codes. These parameters 2 to the m, 2 to the m minus 1 minus m, 4. First of all, we can see that the parameters are the same. In BCH, we have also 2 to the m, the block length, 2 to the m minus 1 minus m as dimension, and the minimum distance is s plus 1, which is 4. But we want to show that not only the parameters are identical, but also their set of code words is identical. So let's understand what requirements we have for BCH of M3. So we have our variables, the values of our polynomial in all different points. These are variables of the code word. And the equalities are that the sum of all A of alpha is 0. This equality is obtained by requirement that the leading coefficient is 0. And then the second requirement is that the sum of alpha times A of alpha is also 0. This is M equations requiring that this next coefficient is also 0. So let's just write down the matrix of this system. So the column corresponds to our variables. So these are our column. So the first one is just the equation where all the coefficients are ones. So we sum up all the variables. And this one is the sum of variables multiplied by some columns. Each alpha is represented as a column of bits, where the column is obtained from alpha. We just express our alpha through some fixed basis or O of f to the m over f2. And because we sum over all different alphas, we do not need actually to fix how which basis is used, because anyway this ranges over all possible columns of height m. So that means that this M equations has the following matrix: 0, 0, 0, 0, 0, 1, 0, 1, 0. So we just list all possible columns of height m. So this will be the parity check matrix of our code. I mean BCH of M3. So this is the matrix defining the linear space of all code words. And you see that this is the same matrix as for this Hamming code. Because in that Hamming code, we have also listed all non-zero, all possible columns, different columns of height m, and also added one new row consisting of only ones. So both codes have the same parity check matrix, and hence the codes are the same. Так, ну вот я вроде рассказал. Ну, задавайте вопросы, потому что я сейчас дам этот самый тест. И в ваших же интересах понять, чего там было неясно в предыдущем. Сейчас, Вероника Алешина, готова писать тест уже? Что-то я не слышу, что вы сказали. Михаил Кошелев, готов писать тест?
Кажется, да. Не знаю.
Ну, хорошо. Я вам дам больше времени на тест, потому что мы раньше закончили. Я сейчас не хочу начинать новую тему, потому что все равно у меня в запасе только 10 минут. Так, сейчас дам ссылку. Так, ну посмотрите, открывается. Ой, я только Веронике послал почему-то. Сейчас. Так, вот всем послал. Так, открывается тест?
Да, все в порядке.
Угу. Ну все, значит, вот в 2 часа конец. Так, все уже сдали, 8 человек было, 8 сдано. Так, это уж какие-то странные люди пошли. Не, Юдаков и Лтаину не
Нет,
странные.
еще не все сдали, еще не все.
Не все? Да. Просто вот, например, Чиняева вообще нету. Его работа пришла. Я ее не буду засчитывать.
Он просто вышел уже.
А, он уже вышел. А. Ну ладно, хорошо. Значит, осталось у вас 3 минуты. Так, ну сейчас 10 человек сдано. Так, ну что, минута осталась уже. Минуты 10. Так, есть кто-нибудь, кто еще пишет, не сдал?
Да, я сейчас допишу.
Ага, есть. Так, ну все, значит, Луценко тоже сдал. Тогда все. До свидания.
До свидания.
До свидания.
До свидания.